Welcome to a short video summary of our 5th year Masters project. With more drones being used in both civilian and military spaces, there are increasing security risks posed from people using them with malicious intent. Drones are often used to disrupt airport traffic and can cause significant damage. In these situations, drones are difficult to neutralise with current methods, so a new tracking method using SNNs for stabilisation could combat these challenges. In this short video, I'll give a basic overview of our SNN control Segway robot and image tracking stabilisation system along with some of the challenges faced. The robot frame was designed to be of minimal weight while still being large enough to house all of our components. The frame was constructed using laser cut acrylic sheets, 3D printed plastic, and steel threaded rod. Stepper motors were used due to their high torque nature as well as their ease of implementation compared to encoded DC motors. When operating successfully, the behaviour of the system is analogous to that of a drone either hovering or in flight. Spiking neural networks are a brain-inspired architecture that use asynchronous spike trains to carry information. These spikes are non-differentiable and so typical gradient descent methods cannot be employed. Using an SNN model for adaptive PID control stands to significantly reduce the power requirements and increase the reactiveness compared to a traditional implementation. A dynamic vision sensor was used as a low-power alternative to a traditional frame-based sensor. This meant that the tracking system was not required to process large amounts of redundant data. To keep the implementation small and low power, we used a Raspberry Pi 4 to handle the intake and processing of DVS events. To enable tracking in real time, we required a subsystem latency of less than 1 millisecond. This was achieved using a simple mean shift algorithm which could track several objects at once. The DVS camera is mounted to the self-balancing robot using a brushless motor gimbal. This allowed it to be positioned independently using object position data sent from the tracking system. Brushless motors were chosen over servo or stepper motors due to their smoother operating nature and reduced vibration. The gimbal was designed to be 3D printed to allow for rapid prototyping and used standardised parts and assembly to make construction simple. This project has served as a preliminary investigation into the implementation challenges which are faced when using SNNs for adaptive PID control. Further work is required to test the combined integration of our subsystems. However, the work performed to date suggests that once better development platforms are available, SNNs will be extremely advantageous when used in fully asynchronous systems. The hardware is the main limiting factor of this system due to the speed at which data can be loaded on and off the FPGA. Hence, reductions in computational time are outweighed by the cost of transferring between spiking and non-spiking systems. Thank you for watching this short summary of our 5th year group project.